Introduction to Thermochemistry. In this video, we'll talk about what is internal energy, what is enthalpy, just a few basics about these. So let's start with introduction first. So thermochemistry, like the name tells you, thermo means energy. Thermo basically stands for kind of like heat, which is a form of energy, and chemistry means chemical reactions. So thermochemistry is that branch of chemistry which tries to study the relationship between chemistry and energy. So what is the energy involved in a chemical reaction? That is studied by thermochemistry. Just to get to basics, what is energy? Energy is the capacity to do work or transfer heat. If any object, any chemical species has energy, only then they can do some work or they can transfer heat. Energy can have several forms. Okay, the two major categories are kinetic energy and potential energy. Kinetics basically means movement, motion. So kinetic energy is the energy of motion. Whenever any object is in motion, it is moving, it has kinetic energy. Potential energy, like the name tells, it's the potential, meaning it's the inherent energy that a substance has because of its either the position or its composition. Okay, for example, any chemical, like if I take gasoline, right? We store gasoline that due to its chemical composition, due to its chemical bonds, it has some energy inside the molecules, and that energy is called the potential energy. So when potential energy is basically the energy that is stored in an object. So energy when things are not in motion, when they are not moving, stored form of energy in any object is called potential energy. Okay, we can further classify these energies into multiple other forms. For example, there's something called as thermal energy, the energy which is associated with temperature. Okay, so the objects that are at high temperature would have high thermal energy, or they would have high heat, right? And the objects that have low temperature would have low energy. When a high temperature object comes in contact with a low temperature object, in that case the heat is transferred from the high to the low temperature until they both reach the same temperature, and that same temperature is called as thermal equilibrium. So heat is a flow of energy caused by difference in temperature. So that's thermal energy. Other forms, for example, chemical energy, the energy that is present in the molecule because of its position, electrons, nuclei, protons, all of that energy that's inside the chemical species because of its bond is called chemical energy, which is basically potential energy, right? Other forms you might have heard of energies like mechanical energy, right, or electrical energy. These are all different forms of energy. For instance, in this figure, you can see this water. In the first image is a waterfall. Water is moving really fast. So this water, which is in motion, has a lot of kinetic energy. And when it is static on top, that is when it has a lot of potential energy. Okay, there are other forms of energy. Always remember law of conservation of energy. This is the first law of thermodynamics. Okay, this is the first law of thermodynamics, which is law of conservation of energy, which means energy cannot be created, it cannot be destroyed. The amount of energy is always fixed, the total amount. Okay, what changes is the form of energy. It goes from one form to another. For example, the water here, if it is not in motion, it is potential energy. When it starts to move, it is converted into kinetic energy. Example, these food, a burger, it has potential energy because of its composition, and when we consume the burger, we get energy from that to do work, to talk, to speak, to breathe, all of that, right? The car, when it is in motion because of the kinetic energy, and what gives it that energy is basically the gasoline. The gas that we fill inside the car, it burns. Gas has some potential energy. When it burns, it converts that potential energy into chemical or mechanical energy, and eventually that causes a car to be in motion, which is kinetic energy. So energy is basically just changing its form. Example, electrical energy, right? That is also a form of energy which is converted into, let's say, light. Okay, so energy cannot be created or destroyed, it only changes its form. Now, what are different units of energy? There are some commonly used units. The one common unit that is used in chemistry is called joules. Joules is 1 kg times meter square over second square. That can be also used as kilojoules. So the difference would be 1 kilojoule, that you already know, should be 10 raised to power 3 joules. Kilo is basically just a prefix. Okay, so one very commonly used unit is joule. Another commonly used unit is calories, which is written as small cal in small letters, lowercase. What is a calorie? It is the amount of energy that is needed to raise the temperature of exactly 1 gram of water by 1 degree Celsius. Okay, and it is equal to 4.184 joules exactly. So these are your conversion factors that you can use to convert between two different units of energy, joules or calories. Now remember, this calorie that we are talking about, small calorie, this is not the food calorie. Okay, when we talk about how many calories are present in a food item, nutritional calories, that is not this small calorie, that is given by capital calorie. Okay, so that C is written in cap, so uppercase. That is called food or nutrition calories. Okay, and the difference between small calorie and capital calorie is that 1000 small calories is equal to 1 capital calorie. Okay, so that is the difference. Or you can say 1 kilo calorie, small calories, is equal to 1 capital calorie. Okay, so the food calorie and this calorie of small calorie is slightly different in their units. Okay, whenever we talk about energy, it's very important to understand two things here. One is called the system, another one is called the surroundings. What are system and surrounding? For instance, if I take this, let's say, an insulated container, this container is completely insulated, and I have this hot piece of metal in here. Okay, this is a hot metal, and I'm interested in what is happening to energy of this piece of metal. The species that I'm interested in, the reaction or the chemical species or the object that I'm interested in, is called as your system, and everything surrounding that is referred to as the surroundings. Okay, so system is the species or the reaction that you're interested in, and surroundings are everything around that system that can interact with this system, that can have energy transfer or heat transfer with the system. Those are called as surroundings, and everything combined together, so system plus surrounding, is called as the universe. Okay, so universe is the whole thing, system is what I'm interested in. Okay, for example, I'm interested in learning how what is the temperature of this object, or how is the heat transferred from a reaction. So that is my system, and everything that can come in contact with the system, that can interact with the system, that can have heat or energy transfer from the system, that is called as the surrounding. So anything that is involved in heat or energy transfer. Okay, so the source of energy, such as a container with a chemical reactant and product, is the system, and the rest of the universe around it is the surroundings. Okay, for example, if I take a cup of coffee, okay, this is coffee, a hot coffee in my hand, then my hand basically, let's make a very, oh no, let's make like a somewhat a resemblance of a hand. Okay, so if this is my hand, this is the cup of hot coffee, I am holding this in my hand, so this, and I'm interested in where is the energy transferring from the coffee. So coffee is my system, and because all the heat from the coffee is transferring to my hands are the surroundings. Okay, so whatever you are doing whatever system I'm interested in, everything around that interacts with the system is the surrounding. Now we can classify systems into 3 different categories. The first one is called as an open system, closed system, and isolated system. These are the 3 systems. What does it mean by open, closed, and isolated? The difference lies in what they can exchange with their surroundings. Okay, so remember, all 3 of these are systems. Okay, and everything around them is surrounding. There are 2 things that a system and surrounding can exchange. One is called energy, another one is called mass. Energy basically means heat, mostly. The energy that is transferred between 2 objects is usually in form of heat. And the other thing that can be transferred is mass. So when both matter and energy can move between the system and surrounding, that is called as an open system, meaning it's open to the surroundings. Mass can transfer, mass means matter, or heat can also transfer between the system and surrounding. That is called open. Example, kind of like a fireplace, right? When wood burns in the fireplace, let's say that wood is my system, but that wood, when the wood burns, heat is given to the surroundings at the same time. You can see like ashes and other things, that byproducts that come out of burning of wood, all those are mixed with the surroundings as well. So both mass and energy can be exchanged. A closed system is the one where only energy but not matter can move between the system and surrounding. So I can pass energy out of the between the system and surrounding, but no mass. Mass cannot be exchanged. It's closed for mass. Example, pressure cooker, okay, or like instant pot. Whenever we are cooking food inside of it, usually the heat can be transferred inside and outside of the cooker, but the food does not come out of the instant pot, or food does not come out of the pressure cooker until unless you kind of open that up, right? Then the last system is called the isolated system, which is kind of name tells you it's isolated, which means neither matter nor energy can be exchanged between the system and surroundings. Everything is closed. For example, kind of like a thermos flask. Okay, it's not exactly an isolated system, because over time we know that if you put hot food into it, maybe after like 5 hours, 6 hours, 12 hours, it will finally cool down, right? So it's not an ideal system, but that's the best closest system example that you can think of. Thermos, which prevents both matter transfer and heat transfer. Now another terminology that we should understand and we talked about is work and heat. Okay, so whenever energy exchange occurs between system and surrounding, it occurs in 2 ways. Either heat is transferred between the 2, or work is done between the 2. Okay, what is work? Work is given by the word W. It is the energy resulting from force acting on an object over a distance. Meaning, when you take one object and we apply, let's say, force on this object, and this object needs to move around over a distance, that is called as work done. If your object moves and displaces, changes its position, only then we say work is done. Okay. The next way the energy transfers is through heat. The flow of energy that causes a temperature change in an object or its surroundings is known as heat. Whenever energy is related to temperature of the object, whenever the energy flows because there is a temperature difference between the 2 objects, the energy flow is called as heat. Heat is also given by the word Q. Remember that. So whenever you see Q in thermochemistry, we are talking about heat. So the 2 things that can be exchanged between the system and surrounding, the way matter and heat energy is exchanged, is in term of work and heat. That is the way energy is exchanged between system and surroundings. Now let's talk about how does work flow between system and surroundings. Okay, in energy, whenever we talk about energy, we have to be careful about the signs of energy. Sign basically means Does your energy have a positive sign? Does it have a negative sign? So that's what we'll look into now. Okay, when we specifically talk about just work, work can have a positive sign or a negative sign. Okay, how do we know if the work has a positive or negative sign? That's what we'll look into now. One is, each time when you're wondering about figuring out the sign, what you want to think is, if this work done is increasing the energy of the system or decreasing the energy of the system. If it is increasing, if the energy of the system is increasing, your work is positive. If the energy of the system is decreasing, the work is negative. That's as simple as that. When it decreases, it's negative, and it increases, it's positive. Okay, so again, this work flow is happening between system and surrounding. So let's look at first scenario, when work is done on the system. Okay, so somebody else is doing the work on the system, so system is being worked on. That simply means that the work is positive. Why? Because when work is done on the system, the energy of the system will increase, so work is positive. The sign would be positive, greater than 0. For example, if I assume that my car is the system, okay, and if a person is pushing the car, that means the person is doing the work. The person is the surrounding, first thing. Okay, when a system is the car and a person is pushing the car, the person is the surrounding, the system is the car. If the person is pushing the car, who is doing the work? The person is doing the work, and the system is being worked on, which means the energy from the person is going to the system, so energy of the system increases, which means this work is positive for the system. And we only and only think about the system. We do not think about surroundings. We do not think about the signs of the work for surrounding. We only think about system. Okay, so it would look something like this. Surroundings are doing the work on the system, which means energy of the system is increasing, so work is positive. Okay, the second scenario is when work is done by the system, so the system is doing some work. In that case, what is happening to system's energy? It should decrease because system is working, which means W will have a negative sign. Okay, for example, again, if the car is a system, in that case, if the car hits a person, okay, so the car is the system and person is the surrounding. So if the car is hitting a person, that means the car is doing the work. So your system is going to be losing energy. Car is losing energy. That is why this work is negative. Okay, for instance, it would look something like this. The system is doing the work on the surroundings. Okay, or the system is doing the work, so work is done by the system, which means energy of the system will lower because it's doing the work, so the work will have a negative sign because the energy is lowering. Whenever the energy is lowered, it has a negative sign. Whichever condition causes the energy to increase, then it would have a positive sign. That is how simple this is. Now let's look at the same thing but in terms of heat. Okay, so heat is also transferred between system and surrounding. Same process. Heat is given by the symbol Q. Now Q can have a positive sign or a negative sign. Again, this would depend on if the heat causes the energy of the system to increase or decrease, and that would be positive or negative. The first scenario is heat is added to the system, which means I'm adding more heat to the system. The temperature of the system will go up. Okay, in that case, Q is positive. Example, if we assume ice is our system, ice gains heat when a person is holding it in his hand. So ice is the system and person is the surrounding, right? So if the person is the surrounding, the person is losing the heat and ice is gaining the heat. So in that case, system is gaining energy, which means it is going to be positive. Look something like this. Surroundings, system. Surroundings are giving heat to the system, so energy of the system will increase, which means Q is positive. The second scenario would be opposite, where heat is released by the system. So system will lose the heat, give it to the surroundings, and Q is going to be negative in this case because system loses heat, so system's energy goes down. Example, a bowl of cold water left in the freezer. Okay, if we take a cold bowl of water and we put it in the freezer, over time the water will lose the heat, right? Water loses heat, and that's when it cools down and it becomes ice. So if my cold water is my system, it is losing heat to the surroundings, which means it has to have a a negative sign so that energy goes down. Would look something like this. Heat goes from the system to surroundings. This is when Q is negative. Now let's try some questions. This is how the questions would look like. Determine whether the value of W or Q determine whether the value of W or Q is positive or negative in each of the following scenarios. Scenario number 1 is a person rolls a bowling ball. A person rolls a bowling ball across the floor, where the bowling ball is defined as the system. Define the sign of W. So who is my system? The ball is my system. A person is rolling the ball, which means ball is being worked on. Who is doing the work? The person is doing the work. Ball is just rolling. Okay, so system is being worked on, which means W will have a positive sign. Let's try B. A person rolls a bowling ball across the floor, where the person is the system. So if the person's a system, when the person rolls the ball, they have to do the work. The person is doing the work, and person is the system, which means the system is doing the work. If system is doing the work, the system will lose energy, which means this work is negative in sign because it's losing energy. Next is C. An ice pack is placed on a person's sore throat, where the ice pack is defined as the system. So if ice is system, the person will be the surrounding. Okay, what will happen to the ice pack? The ice pack slowly melts. Why? Because ice pack gains energy, right? So the ice pack is gaining energy, which means because of this, which means heat. Ice pack is gaining the heat. The question is asking define the sign for Q. So it's gaining heat, which means Q is going to be also positive. Now, the next concept in thermochemistry is going to be internal energy. What is the internal energy? Internal energy is given by the symbol either E, or sometimes it's also given by the symbol U. So either or is used, E or U. Okay, what is internal energy? It is defined as the sum of all the kinetic and the potential energy of an object. Okay, if I'm talking about a system, if this is my system, the total energy that is present in the system, that is called its internal energy, E or U. In this slide, we'll majorly be using it as E, but if you see something used as U, that is also fine. Okay. Absolute values of E are very difficult to determine. Like, it's very difficult to tell how much total energy any object has. So instead, what do we study? We study changes in internal energy. Those are the ones that are more commonly measured. What is change in internal energy? It's given by the symbol delta E. That is its abbreviation. What is delta? Delta is basically this triangle shape that we draw, that is referred to as delta. And E basically stands for internal energy. Okay, And how does this work? Always delta E is going to be E final minus E initial. The final energy of your system minus the initial energy of the system. And always remember, we are only interested in the system. We are not talking about surroundings. We only are interested in the system. That is why it's called the system, whatever you're interested in. Okay. So change in energy, internal energy is going to be E final minus initial, total E final minus total E initial. Okay. Second thing is, remember, energy is always exchanged between the system and surrounding through two things. One is heat, another one is work. So that is why change in energy will always be equal to heat plus work. It's always a sum of heat and work. Only important thing here is we should know the signs of Q and W. Is it positive or is it negative? And here are all the signs. So Q, again, this is all about system. Okay, so Q is, if the system gains heat, it's positive. If system loses heat, it's negative. For work done, same scenario. If work is done on the system, it's positive. If work is done by the system, it is negative. Same thing for internal energy. If the system overall gains internal energy, delta E will be positive. If overall it loses internal energy, delta E would be negative. And how do I calculate overall? It is going to be sum of heat and work. So Q plus W is delta E. Okay. Let's try some questions based on this approach. Wood is burned in an open fireplace. The reaction releases 250 kilojoules of heat and does 15 kilojoules of work on the surroundings. Calculate delta U for this reaction. What is delta U or delta E? Again, remember, same thing, is Q plus W. It is a combination of heat and work done. So the reaction that I'm interested in releases 20 kilojoules of heat, meaning it lost this much heat. So what would be the sign of Q? Q will be negative, which means in this case my heat is negative 250 kilojoules because it was lost. Plus this reaction, question says the reaction does 15 kilojoules of work, which means reaction is doing the work. If it is doing the work, again the sign for W will also be negative. So that is why my W is negative 15.0 kilojoules. Now only thing you do is you add everything together. Okay, this is negative, this is negative, 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 total will become positive, which gives you a total of, oops, my pen is not writing well. The total is going to be negative 275 kilojoules. Okay, I'm sorry, may fix my pen in a minute, but in the meantime it is negative 275 kilojoules of heat change in internal energy, which means the internal energy will drop, which makes sense because system is doing the work and system is releasing the heat. So overall energy of the system should go down. That is why my internal energy is negative. Okay, let's talk about another terminology which is referred to as a state function or a path function. What is a state function? It is basically just a way to represent some mathematical functions. So a state function is a mathematical function whose result depends only on the initial and the final conditions. It does not depend on the process that was used. What that means is, for instance, if let's take example of this hike. If there are two people who are going on a hike, it's the same mountain, they start from the very bottom at the same height, and at the end they have reached to the top of this mountain at the end of their hike. Person 1 took this path, okay, which was approximately, let's say, 12 miles, whereas person 2 took a much straighter approach and the path that they traveled was only 5 miles. So if I ask what is the height difference that both of these hikers achieved, that would be the same for both of them. For example, they both started at 0 feet and they eventually ended up at 10,000 feet. So the height difference that they traveled is around 10,000 feet. That does not depend on who took the longer route and who took the shorter route. So it does not depend on the path taken. This height difference just depends on what is the final height, what is the initial height. Those functions are called as state functions. Okay, for example, if let's say I take some water in a pan and I heat it up. Okay, the initial temperature of water is, let's say, 5 degrees Celsius. After heating, the final temperature is, let's say, 100 degrees Celsius. Okay, so what is the change in temperature? Change means delta T. So change in temperature is final temperature minus initial temperature, which means it went up by 95 degrees. It does not depend on how did we heat it. Did we heat it in one go? Did I stop heating it in the between and lower the temperature and then started raising the temperature again? So these are called as state functions. Why do we care about it? The internal energy that we are talking about, delta E, it is also an example of a state function. It does not depend on what path was taken. It only depends on what is the final energy and the initial energy of the system, and that gives you the change in energy. So that is a state function. Contrary to it, there are some functions that do depend on the path taken, and those are called as the path functions. So they basically depend on what steps were taken, what was the sequence of those steps. It not only just depends on the initial and the final state. For example, work and heat, these are all path functions, right? So for example, for the same last hiking example that we saw, if I ask how much work was done by person 1 versus person 2, then those would be different from each other, because person 1 took a longer route whereas person 2 took a shorter route. So the work done is different for both of them, even though they reach the same height. Those functions are called as path functions. Okay, the next property or the next function that we are going to talk about is called as enthalpy. This is the one of the more important functions that we use in thermochemistry. What is enthalpy? Enthalpy is a state function that relates internal energy, pressure, and volume. Okay, so basically most of the chemical reactions, when these are done in a lab, they are done in an open system, right? For example, if I'm doing a chemical reaction, I probably will be doing this reaction in a beaker. I will add reactant number 1, I will add reactant number 2, and this reaction will be occurring here. So it's an open system, so both heat and work can be exchanged between the system and surroundings. So most of the times when we are working under these conditions, we are working at a constant pressure conditions, meaning constant under 1 atmospheric pressure condition, because it's open to atmosphere. That function is called as enthalpy. When we talk about the heat that is involved in a process at constant pressure, it is called as enthalpy. It is given by this formula: H is U plus PV, or you can say H is E plus PV. Internal energy plus P times V. P is the pressure, V is the volume. So if we are working at a constant pressure, the change in enthalpy is going to be change in internal energy plus pressure times change in volume. Why change in volume? Because the pressure is constant, so there's no change in pressure. That's why I did not put a delta in front of P. This is just a derivation. I'm just trying to show you, okay, something here. So what is delta U? It is, we know from before, delta U is Q plus W. So if we plug that value here, delta H becomes Q plus W plus PV. I just replaced U with this expression. Now what is work done? Work is also minus P times delta V. So we can replace W here, P times delta V with a W. So that becomes negative W here. Positive W and negative W cancels each other out, which basically tells us that delta H is equal to heat at constant pressure. So if a reaction is being done at a constant pressure, the amount of heat that flows from system and surrounding is called the enthalpy. That is it. Okay, so when most of the times when we are doing our chemical reactions in an open system which is open to atmospheric pressure at a constant pressure, in these conditions the delta H, if I'm interested in finding what is the enthalpy of a reaction, it is same as the amount of heat that was traveling between this reaction and its surrounding. So just remember this, that at constant pressure heat is same as the enthalpy. Now based on the heat that is transferred, based on the heat Q that is transferred, we can classify reactions as either endothermic or exothermic. Endothermic, what is that? Endo means enter, endo is coming from the word enter. Thermic means heat. So when heat enters into a reaction, when reactions absorb heat from the surrounding, those are called as endothermic processes. In those cases delta H is always going to be greater than 0, it will be positive. Why? Because they are absorbing the heat. So when they absorb heat, it basically increases the energy of the system, so delta H is positive. Another process is called exothermic. Exo comes from the word exit and thermic comes from the word heat again. When heat exits a reaction, meaning when reactions that transfer heat to the surrounding. So if this is my chemical reaction, this is where the reaction is occurring. If heat goes out of this reaction into the surroundings, that is called exothermic. In this case delta H is always going to be negative, it is going to be less than 0. Okay, for example, the cold packs that we use, right? If somebody gets a burn or if somebody harms themselves, right, like a muscle pain or something, we usually use something called as a cold pack. What is a cold pack? When you apply the cold pack, it absorbs the heat from the hands or the knee or wherever you're using it, right? So it absorbs the heat from the surrounding. So this cold pack is basically an endothermic reaction is happening inside. That is why it is able to absorb heat from the surroundings. Whereas when you're burning like stove top, you're burning wood, you're burning gas, all of that is an exothermic reaction, because when the reaction occurs it releases heat, so we use that heat to warm ourselves, right? So that is an exothermic reaction. Usually how can we show an exothermic or an endothermic reaction using energy diagram? These are called as energy diagrams. So for example, this is time on the x-axis, this is energy on the y-axis. If this is the energy of the reactant and this is the energy of the products, reactants have less energy, products have more energy, which means when the reactants convert into products, they have to absorb all this extra energy. Reactants will have to gain energy, only then they can turn into these products. So this is a reaction which is endothermic. Reactants are absorbing energy, so delta H is going to be positive, so it's endothermic. Whereas in case of the other reaction, for example, one on the right side, this is where the reactants are, this is energy of reactants, this is energy of products. So reactants have more energy. When they want to convert into product, they have to lose all that extra energy, and that extra energy will be released. Those are called as exothermic reactions. Delta H is going to be a negative sign, it will be less than 0. For instance, let's try a question. Wood is burnt in an open fireplace. The reaction releases 250 kilojoules of heat and does 15 kilojoules of work on the surroundings. Determine whether this reaction is endothermic or exothermic and calculate delta H for this reaction. When wood is burnt in the open fireplace, the reaction releases this much of heat. So it is releasing heat, which means Q is lost, right? When it is lost, it is negative 250 kilojoules and does 15 kilojoules of work. So the reaction is doing the work, so W is also going to be negative 15.0 kilojoules. Determine whether this reaction is endo or exo. Because the reaction is releasing heat, it is exothermic, exiting the heat reaction. calculate delta H for this reaction. What is delta H? We know delta H for a reaction is equal to the Q for that reaction if it is done at constant pressure. Wood is being burnt in an open fireplace. That means it's open to air, so it's under 1 atmospheric pressure, which is not changing. So heat here is going to be equal to delta H, and what was the heat? It was negative 250 kilojoules, and that is it. Delta H is here 250 kilojoules.